You know that neat grid of elements from chemistry class, the periodic table? It looks so perfect, so organized, like it was always meant to be that way. But the truth is, it was born from total and utter chaos. For decades, chemists were basically lost, discovering new elements left and right with no map, no system at all. This is the story of how science found the ultimate pattern.
So, picture this. It's the mid-1800s, and the list of known elements is just getting longer and longer. 63 of them, and each one has its own personality, its own properties. But how do they all fit together? Is there some kind of hidden logic? Well, at the time, nobody had a clue. It was like trying to build something with a giant pile of Legos, but with no instructions. It was holding back the entire field of chemistry.
So here's our game plan for this explainer. First, we'll dig into the big problem chemists were facing. Then we'll look at the first clever, but flawed, attempts to find a pattern. After that, we'll get to the main event, Dmitri Mendeleev's incredible breakthrough. We'll even see how he basically predicted the future. And finally, we'll uncover the one missing piece of the puzzle that even he couldn't find, which led to the perfect table we use today.
All right, let's start with the problem itself, because this wasn't just about making things look tidy on a chart. This was a massive roadblock for actual scientific progress. Just look at the numbers here. Back in 1661, we only knew about 13 elements. Fast forward a little over a century, and that number nearly doubles. But then, look at that jump to 1865. 63 elements. The pace of discovery was exploding, and the problem of organizing all this new information was getting more and more urgent every single year.
So how do you even start to solve a puzzle this huge? Well, you look for little hints, small repeating patterns, and a few really sharp chemists started to find the very first clues. The first real aha moment came from a German chemist, Johann Dobereiner, way back in 1829. He noticed something really cool. He found he could group certain elements into little families of 3, which he called triads. And not only did these 3 elements act alike, but their atomic weights were connected by a surprisingly simple math rule. This is a perfect example of what he found. Take lithium, sodium, and potassium. Chemically, they're super similar. They're all very reactive metals. Dobereiner looked at their atomic weights. Lithium is 7, sodium is 23, and potassium is 39. And here's the magic. If you take the weight of the first one, lithium, and the last one, potassium, add them together and divide by 2, you get 23.0. That's the exact atomic weight of sodium, the element in the middle. This was a huge deal. It was the first real proof that there was some kind of deep mathematical order hidden in the elements. But, science almost never gets it right on the first try. Dobereiner's triads were a fantastic clue, but his system just didn't work for all 63 known elements. So the hunt continued. The next big idea came from an English chemist named John Newlands, and while his idea also had some major flaws, it added another critical piece to the puzzle. Now, this idea was definitely creative. Newlands was a music lover, and he suggested that if you line up the elements by their atomic weight, their properties start repeating every 8th element, just like notes in a musical octave. He was the first person to suggest a periodic or repeating pattern across the whole list. Unfortunately for him, the scientific community pretty much laughed him out of the room. Why? Well, his idea had some serious issues. It really only worked for the first 56 elements or so. Crucially, it was way too rigid. He didn't leave any empty spaces for elements that hadn't been discovered yet. He ended up forcing elements that were totally different into the same groups, and even had to cram 2 elements, like cobalt and nickel, into the same box just to keep his pattern going. So these early attempts, with their little victories and big mistakes, they all set the stage perfectly for the hero of our story. Enter the Russian chemist Dmitri Mendeleev, the guy who was finally going to crack the code. So what Mendeleev did was take the best ideas from the people before him, arranging elements by atomic weight, looking for those repeating properties, and he turned it into a formal law. He confidently stated that the properties of elements repeat in a predictable, periodic way based on how much they weigh. But right here, this is what separates him from everyone else. This was his genius move. Unlike the others, Mendeleev wasn't a slave to the numbers. He realized that the chemical properties, how an element actually behaves, that was the most important thing. If lining them up by weight meant putting a super reactive metal next to a totally inert gas, he knew something was wrong. So he made a brave choice. He let the element's character, its family resemblances, be his guide.
And this is where the story goes from just being clever to being absolutely mind-blowing. Because Mendeleev was so confident in his system that he did something nobody had ever dared to do before. So what was it? What was the move that took his table from just a useful chart and turned it into one of the greatest predictive tools in the history of science? He left gaps. On purpose. When an element didn't seem to fit the pattern, he didn't try to force it. He said, no, the element for this spot is missing. It exists, we just haven't found it yet. And then he took it one giant step further. He actually predicted the properties of these missing elements. Just look at this. This is the proof. He left a gap under aluminum and called the missing element eka aluminum. He predicted its atomic weight would be around 68 and its density about 5.9. A few years later, in 1875, a French chemist discovers a new element, gallium. And its atomic weight, 69.72. Its density, 5.94. I mean, come on, his predictions were practically perfect. This wasn't just organizing data. This was like looking into a crystal ball. And if that wasn't incredible enough, he even predicted what it would be like. He famously said about his eka aluminum, "If I hold it in my hand, it will melt." Sure enough, the melting point of gallium is just about 30 degrees Celsius. It literally melts from the warmth of your hand. It was just an astonishing confirmation of his table's power. So, Mendeleev's table was a total triumph. It organized all of chemistry and literally predicted the future. But there was one tiny, nagging little problem he could never quite figure out, a little flaw that pointed to an even deeper truth. This was the anomaly. Take a look at tellurium and iodine. Tellurium's atomic weight is 127.6. Iodine is actually a little bit lighter at 126.9. So if you're going strictly by weight, iodine should come first. But Mendeleev knew from their chemical properties that tellurium belonged with one family and iodine belonged with another. So he swapped them, breaking his own main rule. He knew in his gut it was the right move, but he had no idea why. The answer finally came in 1913 from a young physicist named Henry Moseley. He discovered that the true fundamental property of an element wasn't its weight at all. It was its atomic number, which is just the number of protons in its nucleus. Think of it like a unique ID number for every single element. And this was the beautiful final piece of the puzzle. When you arrange the elements by their atomic number, by their proton count, that whole tellurium-iodine problem just vanishes. Tellurium has 52 protons, iodine has 53. The order is perfect. This discovery gave us the modern periodic law, which says properties repeat based on atomic number, not weight. And that's what gives us the flawless, perfect table we all know today. So, from a jumbled mess of 63 elements to a predictive map of the entire universe, the story of the periodic table is really a story about the search for patterns. It organized everything we knew, and even told us what we hadn't found yet. It really makes you wonder, doesn't it? What new discoveries, maybe even new physics, might change how we see this amazing chart in the next 100 years?